On June 29, 2012, a continuous line of convection traveled 700 miles in 10 hours from Indiana to the Atlantic coast. At 10:47 p.m., wind measurements at Dulles International Airport recorded sustained speeds of 71 miles per hour with gusts exceeding 91 miles per hour. Within 22 minutes, the electrical distribution grid serving Washington, D.C. and Northern Virginia experienced catastrophic structural failure across 83% of its service area. The Mid-Atlantic Electrical Grid in 2012 operated under the National Electrical Safety Code standards established in 1977. Distribution poles supporting 12 kV to 34.5 kV lines were designed to withstand straight-line wind loads of 56 miles per hour in moderate exposure zones. Most utility poles in the Virginia and D.C. corridor were Class 4 Southern Yellow Pine with an average service life of 38 years. The regional transmission network relied on steel lattice towers for 230 kV and 500 kV circuits, engineered to ASCE 7-4 standards with survival wind speeds of 90 miles per hour for a 3-second gust. The system assumed wind events would be isolated and transient. No provision existed for simultaneous loading across multiple interconnected substations spanning a 200-mile corridor. The operational doctrine separated distribution failures from transmission failures. The doctrine did not account for progressive mechanical collapse propagating along the entire regional backbone within a single event window. The atmospheric setup began on June 23 with the establishment of a 594 decameter ridge over the central United States. Surface temperatures across Indiana, Ohio, and West Virginia exceeded 95 degrees Fahrenheit for 6 consecutive days. The air mass stagnated under subsidence inversion with precipitable water values below 1.2 inches. On June 29, a weak surface low tracked eastward along the Ohio River Valley, creating a stationary thermal boundary between the overheated continental air and a cooler marine layer advancing from the Atlantic. By 3 p.m., convective available potential energy exceeded 4,000 joules per kilogram across southern Indiana. A mesoscale convective system initiated along the boundary at 3:45 p.m. The system organized into a bow echo structure with a leading gust front propagating at 60 miles per hour. The rear inflow jet accelerated as the system entered Ohio, reaching peak intensity at 6:30 p.m. with forward speed of 70 miles per hour. At 7:12 p.m., the National Weather Service radar at Wilmington, Ohio, detected a bow echo signature extending 240 miles along a southwest to northeast axis. The reflectivity core exceeded 65 dBz with velocity couplets indicating embedded mesovortices. The gust front crossed into West Virginia at 8 p.m. with measured surface winds of 74 miles per hour at Yeager Airport. Standard severe thunderstorm warnings were issued with lead times between 18 and 34 minutes. The warning specified damaging winds but did not classify the event as a derecho until retrospective analysis. At 9:40 p.m., the system entered Loudoun County, Virginia, with forward speed increasing to 82 miles per hour. The radar presentation showed a solid line of 70 dBz returns with no breaks or weakening signatures. Automated weather stations recorded pressure falls of 6 millibars in 11 minutes. The system maintained coherent structure across the entire Appalachian ridgeline without orographic disruption. The derecho maintained continuous linear propagation from Indiana to the Atlantic coast over a period of 10 hours and 14 minutes. The unbroken track length measured 714 miles. Peak wind gusts were recorded at 91 miles per hour in Fort Wayne, Indiana, 88 miles per hour in Columbus, Ohio, 81 miles per hour in Morgantown, West Virginia, and 91 miles per hour at Dulles International Airport. The system did not weaken or reorganize. Each successive jurisdiction experienced the same wind magnitude within a 15-minute transit window. The electrical grid in each affected region operated under independent utility management with minimal real-time coordination protocols. As the derecho moved eastward, transmission operators in Virginia and Maryland had between 90 and 120 minutes of advance notice based on upstream failure reports. No preemptive load shedding or system islanding was executed. The continuous eastward progression created cumulative mechanical loading on the 500 kilovolt PJM interconnection backbone, which spans from Ohio to the Atlantic coast. At 10:51 p.m., the 500 kilovolt Loudoun to Dooms transmission line experienced cascade failure when 3 lattice towers buckled under sustained crosswind loading of 87 miles per hour. The line carried 1,420 megawatts at the time of failure. Automatic relay protection isolated the circuit in 180 milliseconds. Load transferred to the parallel 230 kilovolt backbone, which exceeded thermal limits within 4 minutes. At 10:58 p.m., distribution feeders throughout Fairfax County, Arlington, and Alexandria lost primary voltage as wooden utility poles snapped at ground level or failed at crossarm attachment points. Over 2,100 distribution poles failed in Fairfax County alone. The failure mode was identical. Transverse loading exceeded the modulus of rupture for aged pine under combined bending and torsional stress. Dominion Energy reported loss of 83 substations within a 40-minute window. The DC transmission ring, consisting of 6 230 kilovolt lines, lost 4 circuits simultaneously. The remaining 2 operated in emergency overload until protective relays tripped them offline at 11:14 p.m.
The failure of grid power simultaneously disabled 14 public safety answering points across Northern Virginia and suburban Maryland. The Fairfax County 911 Center lost commercial power at 10:53 p.m. Backup diesel generators activated under automatic transfer switch protocol. At 10:56 p.m., the transfer switches for the telecommunications equipment failed due to a known fault condition in the automatic transfer switch controller firmware. The center went fully offline. Call volume during the 22-minute failure window exceeded 1,800 inbound requests. Callers received fast busy signals or dead air. Similar failures occurred at the Prince William County Center, the Loudoun County Center, and the Montgomery County, Maryland Center. The regional 911 network relied on a hub-and-spoke topology with central routing nodes in Vienna, Virginia, and Rockville, Maryland. Both hubs lost power and backup capability. Cellular base stations in the affected corridor operated on battery reserves with a design endurance of 4 hours. By 2 a.m., 68% of cellular sites were offline. The Washington Metropolitan Area Transit Authority lost traction power across all 6 rail lines at 11:02 p.m. The system carried approximately 18,000 passengers at the time of failure. Trains stopped in tunnels and on elevated sections. Emergency lighting operated on onboard battery systems for 90 minutes. Evacuation of passengers from tunnel sections required manual deployment of portable egress ladders and took between 2 and 5 hours per train. Surface streets in Arlington, Alexandria, and Fairfax lost all traffic signal operation. The Regional Traffic Management Center, which coordinates 1,240 signalized intersections, went offline when the primary data center in Fairfax lost power and cooling. By 11:30 p.m., major arterial routes including I-66, Route 7, and the Dulles Toll Road experienced complete gridlock as drivers attempted to exit the region without functional navigation or communication systems. The Virginia State Police reported 340 traffic collisions between 11 p.m. and 1 a.m., a 12-fold increase over baseline conditions. Ambient air temperature at the time of grid failure was 98 degrees Fahrenheit, with heat index values exceeding 104 degrees Fahrenheit. The regional forecast predicted sustained temperatures above 100 degrees Fahrenheit for the following 3 days. Utility repair crews faced thermal work limits under OSHA heat stress protocols, restricting continuous outdoor labor to 45-minute intervals. Each failed utility pole required vegetation clearing, truck positioning, and manual augering for replacement pole installation. Average repair time per pole measured 4.2 hours under ideal conditions. Fallen trees blocked access to 60% of failed poles in Fairfax and Loudoun counties. Road clearing required coordinated deployment of county forestry crews and contracted arborists. Dominion Energy mobilized 2,800 line workers from 14 states. The staging and logistics operation required 72 hours to achieve full deployment. During this period, hospitals operated on generator power. Fuel resupply for generators became critical as regional fuel distribution terminals lost electric pump operation. The Regional Emergency Operations Center coordinated 140 fuel trucks for priority delivery. The Derecho caused loss of electrical service to 4.2 million customers across 6 states. In the Virginia and D.C. corridor, 2.1 million customers remained without power 48 hours after the event. The failure of 911 call centers affected a population base of 3.8 million. During the first 6 hours of the outage, an estimated 4,700 emergency calls went unanswered. The economic loss from industrial and commercial cooling system failure exceeded $1.1 billion. Data centers in Northern Virginia, which host 70% of global internet traffic, operated on generator reserves. 3 facilities experienced generator mechanical failure due to sustained operation above rated thermal capacity. Power restoration followed a prioritized sequence: transmission backbone, critical infrastructure, and residential distribution. Full system restoration required 11 days. The final 80,000 customers in rural Loudoun and Fauquier counties were reconnected on July 10. The PJM interconnection estimated total infrastructure replacement cost at $340 million. On August 3, 2012, the Federal Communications Commission initiated an investigation into the failure of the 911 network during the Derecho. The investigation documented that 14 public safety answering points experienced total service disruption due to loss of primary power and failure of backup generator transfer mechanisms. The FCC issued a Public Safety and Homeland Security Bureau report in November 2012, concluding that telecommunications facilities supporting 911 services lacked enforceable backup power standards. In response, the FCC adopted new regulations in 2014 requiring all 911 call centers and telecommunications hubs to maintain a minimum of 24 hours of battery backup and 7 days of on-site fuel reserves for generator operation. The North American Electric Reliability Corporation revised transmission planning standards to include analysis of sustained straight-line wind events exceeding 80 miles per hour over linear distances of 500 miles or greater. PJM Interconnection implemented a regional coordination protocol for real-time derecho tracking and preemptive system islanding.